All right, guys, so some examples of problems involving ellipses here and the standard form of ellipses. I'm going to start off with this question here, number 4, where they give us a major axis from -6,2 to -6,8. And really what they're giving us there is the vertices. Now, you could definitely draw a little sketch that might help you for this. But this also tells me something else. Since the y values are changing, and picture -6,2 and -6,8 on a graph, this tells me that this is going to be a vertical major axis, right? Because they're vertical, they go up and down, they're above each other. And the first thing we need to do is find, well, kind of two things here. From this, we can find the center of our ellipse. It's going to be the midpoint of these. So I'm going to have that first. So I'm going to find the center. And it's going to be the midpoint of these 2 points. Now, you could go back and use our midpoint formula, which I'll write down here, but I'm hoping we don't really feel like we need to use that and think about it every time. But you take the average, you add up the x's, and you add up the y's and cut them in half. But for this one, our midpoint is still going to be at -6, right? That's halfway between. And then I like to think -8 and 2 are 10 units apart. So 5 units from one of these is going to be the midpoint. So that'll be at -3. Also, while doing that, we kind of just found out what the A value is, right? Since half of our major axis is A, so I'm going to say our A value equals 1/2 of the major axis. And same sort of thing. Hopefully we don't have to use the distance formula to figure out how long the major axis is here. For these problems in this section, it's always going to be vertical or horizontal. So from -6,2 to -6, -8 is just going to be how far apart -2 and -8 are. And these are 10 units apart. So A is going to be half of that is 5. All right, so with that in mind, we're going to pretty much do the same exact thing for the minor axis. So here they gave us the minor axis. That's going to help us out with the B value. So B is half the minor axis. This is horizontal, right? From -3 to -9. So our minor axis looks like it's 6 units long, which means B is going to be equal to 3. So I have everything I need for my standard form. We have our center. So I'm going to put that in, x plus 6 squared, y plus 3 squared. And then don't forget earlier we said that the major axis is vertical because those two vertices that they gave us, -6,2 and -6,8, were up and down, were above each other. So since it's a vertical major axis, we're going to put a squared under the y value. So that'll be 25 under there going through, and then b squared would go under x. So that would be our standard form for this parabola. You can always check by putting in a vertex or two to this equation and make sure it equals 1. All right, so that's one example. A lot of the other examples follow along this same method we have going on here. So I'm going to jump down to another important term that comes up for all conics, but we're really seeing it for the first time for ellipses for us, and that's eccentricity or eccentricity. You guys can look up how to say it, but I believe I've looked it up before and it's pronounced eccentricity. But hey, potato, potato, right? And this is going to be kind of the measure of how fat or how football shaped or how circular an ellipse is. So the eccentricity or eccentricity for ellipse is the ratio of C to A. And we usually use the variable e to define it, and it would just be c over a. Now, because of this, it's always going to be between 0 and 1 for an ellipse. So I'll say over here, e is greater than 0 and less than 1. And that's because of the relationship between c and a. Remember, in an ellipse, that we have a squared equals b squared plus c squared. So a always has to be larger than c. And down here, we've got a little kind of demonstration of this. We've graphed a couple ellipses now, and when the focus is really close to our vertex, that's when C and A are very close together. So that'll be an eccentricity closer to 1. Now, as the foci move in closer and closer to the center, right, C gets smaller, so our eccentricity gets smaller. For circles, which we'll do an example of next, there's no foci, right? The center is just what we rotate around to create a circle. So technically, the eccentricity of a circle is 0. And it's kind of up to you or not if you want to say greater than or equal to 0, because technically, if the eccentricity is 0, then your ellipse is a circle. So kind of up to you on that one. It's, a subcategory of our ellipses. So I'm going to do an example, number 10 down here, that has eccentricity in the problem. So this is similar to what we had last time. We're given vertices and the eccentricity. So I'm going to start the same way we did. So these vertices will tell us two things about our ellipse. It'll tell us where to find the center. So I'm going to say midpoint is the center of our ellipse. So that's going to be 5. And then I'm going to use my calculator to help me out here. Well, let's also write out our major axis is going to be, so the distance 24, 28. Well, that's a big ellipse. It's 52 units long. So our A value is going to be equal to half of that, 26. So that's an important measure that we'll need. And then 26 units away from one of these vertices is going to be the center. So it looks like we're at -2, I believe, for that. So we can really start actually creating the standard form for this, and I'll do that. So we're going to have x minus 5 squared, y plus 2 squared, and then we know a is 26. And since the y value changes, right, these are going up and down. So we also know that this is a vertical ellipse. So I'm going to have under y 26 squared. And it's up to you if you want to actually calculate that in the calculator, but so far I haven't needed my calculator, hopefully, so I'm going to leave it at that. All right, now we don't have anything about the minor axis or the b value or the foci, but we do have our eccentricity. And they told us it's 12 over 13. Now we have to be really careful here. This is the ratio of C to A. It doesn't mean that 12 is C and 13 is A. But what we kind of can say about this, since it's a ratio, we know that C and A, I'm going to write it like this, are going to be 12 times something and 13 times something. That's something. That x might be 1, might be 2, might be 1.5, but we can't assume that C and A are just 12 and 13. But kind of lucky for us here, we fortunately do know what A is. We found that using the major axis, so I'm going to sub it in to this portion. A is 26 from over there. And then we can solve through. So in order for this proportion to work out, x has to be 2. So we're going to get a 24 up there and a 26. All right, so with all that information in mind, we have A and C. So we've got C equals 24. We already know A is 26. And we can finally find B using A squared equals B squared plus C squared. So for A squared, I actually have to do 26 squared now. That's going to be 676. C squared, 24 squared equals 576. These work out nice. B squared is 100, and B would equal 10. I really actually only need this guy though, B squared. So I'll wrap up by putting this into my equation, and there is my standard form. So just moral of the story when it comes to eccentricity is that if they give it to us, we can't assume that's what C and A are equal to. We just know it's the ratio of C to A.